Swayam Prabha. Digital India. Educated India.
Hello and welcome to this fifth class on special relativity. In the last class, we saw how the special relativity dictionary or transformations imply a whole host of strange effects that were completely unprecedented. The relativity of time, time dilation, moving clocks appearing to tick slower, length contraction, moving rods appearing to be shorter, and the phase offset that we would expect to see in moving clocks. These effects are completely strange, yet today we will see how all of these follow just from the simple additional postulate in special relativity that the speed of light is the same as measured by all inertial observers. The next thing that we will do is expand upon our dictionary for times and positions and include more words in this dictionary. We will include the transformation for velocities and accelerations. Now, in the last class, I only talked about what happens to clocks which are arranged in the direction of motion and what happens to rods which are placed along the direction of motion. We will talk first about what happens to clocks which are arranged perpendicular to the direction of relative motion and rods which are perpendicular to the direction of relative motion. Now let's perform a thought experiment. Let's suppose that we're in a particular frame of reference S. In our previous example, this is, let's say, the platform. And let's consider two events that occur at, so we'll set up our coordinate system. So let's suppose this is the X direction, this is the Y direction. And now let's suppose that we have an event. And let's suppose we're sitting at the origin. Let's suppose that we detect two events at the same time t, and these events are seen at location y1 on the y-axis, and another location, let's say minus y1 on the y-axis. Now, one way we can tell these are simultaneous, even if we haven't checked our synchronized clocks, is to send light signals. And if we're sitting at the midpoint between these two events, then we will see the light signals from these events reach us simultaneously. So now the question is, if these two events appear simultaneous to us, do they also appear to be simultaneous to an observer who is moving along the X direction? Okay, so now consider a frame S prime, and in this frame S prime is moving to the right at a speed v along the X direction. And we want to know if the events which occurred at coordinates 0, y1 and 0, minus y1 appear to be simultaneous to in the frame S. Do they appear to also be simultaneous in the frame S prime? We previously saw that if the observer is traveling in the same direction, that is, if the observer S prime was traveling in the Y direction, these events would not appear to be simultaneous to observers on a train, say. Okay, but what about if these events are occurring at the same spatial coordinate, but the direction of motion is perpendicular to, if they're occurring at the same X coordinate, but the direction of motion is in the X direction? Now we can easily visualize what will happen. So imagine that O prime passes O at the same instant t at which these events occur, and O prime then continues to go further ahead. Okay, so after some time delta t, they would have moved a distance of v delta t along the x-axis. And now if you also imagine that O prime had some friends who passed the events which were at y1 and minus y1, these friends would send light signals to O prime. Now, these light signals would travel at the speed of light, and eventually they would reach observer O prime. Okay, and these signals would traverse exactly the same distance as seen by observer S on the ground, and therefore observer S would conclude that these two events, these two signals, reach observer O prime simultaneously. Okay, so there is no reason that S prime should also not see these events to be simultaneous. So to conclude, if we have motion of S prime perpendicular to two simultaneous events, or if we have two clocks as seen by the ground observer, that are simultaneous, if the ground observer simultaneously peeks into the clocks of the train observer, these clocks might show different times. So, for example, they show a different time here, but they will be in phase with each other. Okay, so that is, these events which are in the perpendicular direction will appear to be simultaneous, as seen by observer S prime. So as long as S prime is moving perpendicular to these clocks, those clocks will appear to be in sync or synchronized with each other in perpendicular directions to the direction of motion. Okay, so let's write that down. Clocks perpendicular, or clocks placed perpendicular to the direction of relative motion do not have a phase offset. Okay, and we can also see this explicitly from the special relativity transformations. If the motion is only along the x direction, then t prime is, we saw it's gamma times t minus vx over c square, where gamma is 1 over the square root of 1 minus v square by c square. So the new time coordinate, that is the time coordinate as measured in the frame S prime, depends only on the old time coordinates, t, and the x coordinate x, which is the same for both these clocks, and therefore the time t prime on the moving clocks would be the same. Okay, these clocks would agree with each other. They may not agree with the clocks on the ground, and we know that they will tick at different rates from the clocks on the ground, but these clocks will appear to be to have no phase offset from each other. Now let's consider what happens to lengths perpendicular to the direction of relative motion. So let's suppose that we have a rod on a train, okay, which in the frame S prime has a length of let's say 1 meter, and a rod S, which according to the ground observer also has a length of 1 meter. So they could have compared these lengths with each other when S prime was at rest, but now S prime is moving with respect to S at a speed v, let's say along the x direction. And the rods are held perpendicular to the x direction, so they're held, let's say, along the y direction. So this rod is at coordinates y1 and y2, and this rod is at coordinates y1 prime and y2 prime as measured by observer S prime. So the length of this rod, according to observer S prime, would be given by a simultaneous measurement of its y coordinates, and you subtract the difference between them, and that should result in the length of the rod as measured by the moving observer. And similarly, the length of the rod as measured by the ground observer should be y2 minus y1. which is the length of the rod as seen by the ground observer. Now, our special relativity dictionary tells us that nothing special should happen in the direction perpendicular to the direction of motion. So y2 prime should be y2, y1 prime should be y1. And this just came about from the principle of isotropy. There's no preferred direction except the x direction, so it's not clear that anything should happen in the perpendicular direction. And so therefore this dictionary tells us that the lengths of the rods will be measured to be the same. Now what that means is that rods placed perpendicular to the direction of relative motion appear to be of the same length. That is, the observers in frame S will also see that the rods which are moving along with the train appear to have the same length L. However, we saw that this is not true if the rod were placed along the direction of motion. They're placed along the direction of motion. The rod which is moving along the train would appear to be length contracted. Now let's try to understand the same effect from the principles of special relativity. So let's suppose that we have an observer S in a frame S, and they have a rod of length L with them. And let's suppose that there's a moving observer on the train with a rod of length L, according to them in their rest frame, moving with a speed v towards S. And let's suppose that that at the instant that they pass each other, okay, we've arranged for it so that this end of the rod, these ends of the rod just pass each other. What we want to know is, do the tops of the rods also appear to pass each other at that same instant? Now let's suppose we do an experiment by imagining that this rod S prime has a piece of chalk on it, and the rod S has a piece of chalk on it. Okay, and as they pass each other, if the rods, as they pass each other, if the rods or the tops of the rods touch the other rod, they will leave a mark. So now as S prime passes S, if S prime is at least as long as S, a little bit of this white chalk will be left on the rod of observer S prime. And similarly, as S prime passes S, if the rod on the train leaves a little bit of a mark, would leave a little bit of a yellow mark on the static rod or on the rod in the frame of S, if the rod S prime appears to be shorter, or at least as long as the length of the rod L as seen in frame S. Okay. So now let's suppose that, let's just suppose, for example, that it's possible that the rod's length S prime, as seen by the ground observer, is longer than L, or is shorter than L. So let's suppose this rod appears to the ground observer to have a length which is shorter than L. Then what would happen is that as they pass each other, the rod from the train would leave a mark on the rod in the frame S, but the rod on the platform would not leave a mark on the rod in the train. Okay, and the events of the rods passing each other are simultaneous as measured by both the ground observer as well as the train observer. Remember that simultaneity is only relative at a distance along the direction of relative motion. Perpendicular to the direction of relative motion, these events are simultaneous as seen by both observers. That is, all points on the rod appear to pass each other simultaneously. Okay, so now if this were true, that the rod appeared to be shorter as seen by observer S, then observer S will see a chalk mark on their rod, but the moving train observer will not get a white mark on their rod. So according to them, they would have seen that observer S's rod, they would conclude that observer S's rod appears longer to them. Otherwise, it would have left a mark on their rod. And so now we conclude that there would be a way to tell who is in relative motion to whom. Okay, in other words, S would appear to be a preferred frame relative to frame S prime. Okay, or vice versa, because in one of the frames there is no mark left on the rod, but in the other frame there is a mark left on the rod. However, the situation between S and S prime is perfectly reciprocal. They both have rods of length L. In frame S, the frame S prime appears to be moving to the right at a speed v. In frame S prime, the rod appears to be moving to the left at the rod of S appears to be moving to the left at a speed v. Okay, so therefore we would run into a contradiction if we assumed that one of the rods appears to be smaller to one observer, because that would mean that this reciprocity is broken and we can pick out a preferred rest frame. Since that is not the case, we must conclude that rods placed perpendicular to the direction of relative motion do not exhibit any kind of length contraction. Now let's try to understand time dilation intuitively again from the perspective of the postulates of special relativity. So let's consider a static clock in frame S. And one way we can construct such a clock is to imagine what we call a light clock. So now suppose that this rod has, you imagine a setup where I have two mirrors, so one mirror here and one mirror over here, and I shoot a light beam upwards, okay, and the separation between them is known, of some length L, and this light beam goes up and gets reflected back down, and the time it takes to travel up and back down, I call that time 2L by C. Okay, so by measuring how many clicks I register on, so if I wait some amount of time, any light beam that I send up will bounce up and down many times. So if I count how many 2L by C, how many clicks I register, okay, the total time would be number of clicks times 2L by C. Okay, so I can measure time in this way using this device, which we call a light clock. And again, the reason to use a light clock is there's nothing special about a light clock. Everything that we say should be true for any kind of clock that you use to measure things. However, we can be sure about how the light clock appears to behave relative to a second observer, S prime, who is now moving with respect to S at a speed v. Okay, and the reason we can be sure about this is because we know how light appears to behave according to the postulates of special relativity as seen by a moving observer. Okay, an observer moving relative to this light clock. So now let's suppose that we have S prime is also carrying a clock with them. S prime is also carrying a clock, which is also a light clock. And so they send light beams up and down. And let's suppose that the length L that they have is the same in the rest frame of the train. And again, the time that they measure on their clock would be the number of clicks that they see times 2L by C. Now, you might be concerned that if the time interval 2L by c is large, right, then we would only be able to measure time with some resolution, right, because we have to wait for the light signal to actually register a click. But in principle, we can make this length L as small as we like, and therefore we can measure time with arbitrary precision by choosing a small enough length in the perpendicular direction. Now, what we'd like to know is if, let's say, the clock on the train registers one click, that is, it registers a time interval of 2L by c, that is one click, how much time would have elapsed on a ground observer's clock in the time it takes for the train observer's clock to register one click? So what we would see is, if you were in the frame S and you look at this moving light clock of observer S prime, the moving light clock looks like this. There's a light signal that's sent, and the light signal would appear to travel forwards and then down, and the light clock is moving along with this. So the light clock over here is where the light hits the reflecting surface, and then over here is where it comes down and registers click. Okay, so this is what S prime's light clock would look like in the frame S. Okay, and remember that in the perpendicular direction L, the length of the light clock perpendicular to the direction of relative motion would be exactly the same. So both observers would agree that in the perpendicular direction, the light has to traverse exactly the same distance. However, they disagree on the distance traversed by the light in the horizontal direction. According to the train observer, okay, the light has not moved at all in the horizontal direction. It's just gone straight up and down. I've shown it here as separate, but really you should think of this as I sent it straight up and it came straight back down. Okay. Okay, so now we can ask, according to the ground observer, how long does it take for the light signal to go up here, okay, to go up here and then come back down? Now, in the suppose it takes a time interval delta t for this light signal to go up and come back down. In this time, the train or the clock would have traveled a horizontal distance of v times delta t. All right, and now we know in the perpendicular direction that this length is L, okay, and since the situation is symmetric, this distance is v delta t, half v delta t, and this distance is also half v delta t. So therefore, by using Pythagoras' theorem, this is a 90-degree angle, this distance over here is just the square root of L square plus half v delta t whole square. Okay, and similarly, this distance is the same as well. Okay, it's the square root of L square plus half v delta t square. So therefore, the observer on the ground concludes that the light signal that observer S prime sent, or observers on the train sent with their light signal, actually traveled a distance. So distance traveled by the light signal on the train as seen by the ground observer, or as seen on the moving clock, as seen by the ground observer, appears to be twice of the square root of L square plus half v delta t square. But how long would it take for light to travel that distance? Well, we know the answer from the postulates of special relativity. No matter which direction this light beam is traveling, it should be traveling at a speed c as seen by the observers on the ground. It appears to travel at a speed c on the train, but it also appears to travel at a speed c according to the observers on the ground. So therefore, it must be true that this light signal travels at a speed c. So another way to express this distance that the light beam travels, so the distance should also be c times delta t. That is, this expression for the distance should be exactly the same as this expression for the distance. So equating these two, we can actually figure out how much time delta t would have appeared to pass for the ground observer. So equating them, equating these two expressions tells us how much time has passed for the ground observer. Okay, and that time would be 2 times the square root of L square plus half V delta T square over delta T. Okay, so this is the distance that the light beam travels divided by the time it takes to travel that distance. This should be equal to the speed of light. Okay,